Hey, how's everybody doing today? Welcome to class. It's good to see you. Congratulations, everybody. You took care of your first exam in Psych 150. We are 1/4 of the way through this semester, and I am super excited for everybody. I didn't finish grading the exams last night because I was too busy glued to the television watching the Super Bowl. I apologize for that, but I will have all of your exams graded and your grades updated today. Uh, a couple of you, how did we do? uh, you did fine, actually. The grades that I did see looked pretty good, Omar. I'm real proud of everybody so far, and I think all of you are going to be fine as long as you keep turning in your homework and doing your discussion boards. You should be fine in this class. I'm sorry, my throat's really hurting me today. I'm in quite a bit of pain. This freaking cancer treatment is getting to me. We're going to be on a day-by-day basis with lectures. I hope to keep lecturing, but at some point in the next couple of weeks, I'm probably not going to be able to talk anymore. So at that point, I'm just going to be giving you the PowerPoint presentations, and you're going to have to make do. I apologize for this. I've been doing the best I can, and I'm going to keep doing it just as long as I can, but my throat is freaking killing me. Oh. I talked to the doctor today, and he gave me 4 days worth of painkillers. I was like, seriously, dude, 4 days? 4 days? I couldn't help but laugh, but I'm going to be in there begging next week, see if I can get more. So I hope everybody's doing well. Thank you very much. I think Ryan, yeah, actually, that's what I'm going to do, Whitaker. If I can't speak anymore, I'm going to just going to put my old classes in, and you'll just go with those. I'd prefer to do the live class because I kind of like talking to you and having everybody ask questions. It feels more like school to me, and it probably does to you. But if I have to, I'll just go with the old lectures. But I'm going to try to put that off as long as I possibly can because I have too much fun doing this stuff, okay? Ryan, you said you wanted to make an announcement in class today. You have the floor, my friend. Oh, yes. Ryan's family just opened a eatery on Hillsborough Street. Meat and Bite. Sounds good to me. I looked at the menu. It looks tasty. It looks like just the kind of thing that you would want late night if you've been studying or out on Hillsborough Street having fun. As soon as my as soon as I'm able to eat solid food again, I promise you I'm going to be up at the Meat and Bite having dinner there too. Right now I'm on Ensure. It's that protein drink with all your vitamins and whatnot. I'm eating Ensure and mashed peas at this point. But I will definitely be up there trying some of Ryan's family's good food. Yeah, I think it's a great place. Oh, and I definitely will. When I go, Ryan, I expect you to be there so that you and I can have lunch together. In fact, maybe I'll text you, and everybody who wants to meet up there can. So we'll do it as a group thing. Okay. Exams. I will have them graded by the end of the day. And I'm sure everybody did fine. We've got 3 more exams, so 2 more exams and a final, so you've got plenty of time to get your grade up. As long as you keep doing your homework and your writing assignments, you should be okay. Excuse me, your discussion boards. Okay. Ooh, let's go ahead and get this started. Y'all ready to talk? Let's go ahead and do chapter 5. Chapter 5. Okay, so we're going to talk about sensation and perception today. If you want to get a PhD studying sensation and perception, the degree you actually get is what's called an experimental psychology degree. So So the area, the subfield of specialty, remember we talked about developmental psychologists last week. I told you chapter 2 and 3 were all about biological psychologists. The people who study sensation and perception are called experimental psychologists. And that's not because they're the only ones that do experiments. Actually, all kinds of psychologists do experiments. But if you remember from chapter 1, and Gustav Fechner, you'll remember that they were the first ones to do experiments. So that's why they got the label experimental psychology. So if you want to study the sense of taste, touch, whatever, smell, vision, you go get yourself a PhD in experimental psychology. So let's talk about this. Now, the one thing I want you to understand is that that perceiving something, consciously perceiving a sense, involves two particular processes. One we'll call sensation and one we'll call perception. Okay? So sensation is actually recording the pattern of action potentials, the nerve impulses in your brain. So as you're looking at me right now, your rods and cones in your eyeball are transmitting action potentials, nerve inputs to the back of your brain. Getting that input into your brain is what we call sensation. However, there's a second process called perception, and that's making meaning of what you see. So the first time you saw an apple as a kid, you just saw color and shape, but you didn't know what you were looking at. You had to learn that that object you were looking at was an apple. So the process of recording conscious sensory experiences involves sensation and perception. Sensation is controlled by receptor cells that turn external energy into action potentials, and perception is your making meaning out of that, out of those action potentials that come into your brain. So we have all of these different kinds of cells called receptor cells. Remember, I talked to you a couple weeks ago about sensory neurons and motor neurons. Sensory neurons take information to a brain part, and motor neurons is the neurons that carry information from a brain part telling another part of the brain or body to move. But there's actually a third sort of set of nerve cells. We're going to call these receptor cells. And their job is to turn physical and or chemical energy into action potentials. So as you're listening to me right now, the sound waves are bouncing into your ear, and they're causing these hair cells in your ear to vibrate. Those hair cells are what we call receptor cells because they're turning sound waves into action potentials. As you look at me right now, you have my image is falling on these rods and cones. These rods and cones are turning wave information into action potentials. Okay, so they're visual receptor cells. If you touch yourself or somebody touches you, you have somatosensory receptor cells that turn that touch, that pressure, that heat, that pain into action potentials. Right now, my throat is hurting like you would not believe. And I have receptor cells, pain receptor cells in my throat that are feeling the pain of the radiation, and they're telling my brain, oh my goodness, Chris, you are hurting, right? So those are receptor cells. Now, the process by which receptor cells turn chemical and physical energy into action potentials we call transduction, okay? Transduction. This is the process of turning physical energy into action potentials. Does that make sense so far? Okay, so today we're going to talk mainly about vision, and then on Wednesday we're going to talk about all the other senses, okay? So, if you see this little picture right beside me, the physical stimulus, the traffic light turns green, light waves are the physical stimulus. they go into your sensory receptors, your receptor cells in your eyes called rods and cones. Those rods and cones turn that information into action potentials. This is called transduction. That goes to the back of your brain, your occipital lobe, and then that information is shared with all different parts of your brain, and you get the perception of the light turning green. And for each one of the senses that we're going to talk about in your chapter, there's going to be a little chart that kind of shows you the process of how you go from the physical stimulus all the way to perception of the stimulus. Okay? Now, let's talk a little bit about the history of sensation and perception. If you remember from chapter 1, and it was on the exam last night, Gustav Fechner was the first person interested in measuring sensory perception. And I suggested to you that he was the first person to scientifically measure a mental state. Now, he measured this thing called the just noticeable difference, or what we call the difference threshold. This is the smallest amount of change that your brain can perceive. Now, the weird thing is, depending upon circumstances, your absolute threshold, the ability of you to perceive a stimulus, will change. So, can you taste the salt that I put in your food? Well, it depends. If you just ate a salty pizza, you won't be able to taste as much salt as if you just drank a glass of water. If any of you have ever gone into your room at night and turned off the light, you've probably noticed that as soon as you turn off the light, everything goes pitch black dark, and you can't see anything at all. But if you'll wait about 30 seconds, this thing called dark adaptation occurs, and suddenly you can begin to see in the dark. Have any of you ever had that experience before? If you have, okay, well that should suggest to you that your absolute threshold, your ability to sense things in your environment, changes. So your absolute threshold is hard to measure. However, it turns out that your ability to measure change in a stimulus, did that light get brighter? Did that weight get heavier? Did that pizza get saltier? Actually, that doesn't change. Your ability to detect change seems to be about the same. And it turns out that your ability to detect change, let me erase this. Your ability to detect change, it turns out that your stimulus has to change 1/40th of its original intensity for you to detect change. And it was the fact that it was this very systematic number is what convinced psychologists that Gustav Fechner has exactly, it's the just noticeable difference. You know what? Hold on. Let me go ahead and give you a good job, Yasmin, for doing that. Now, the modern subfield's called experimental psychology, and it's how the brain processes and integrates sensory information. Wow, that's impressive, Omar. You know what? I'll have to give you a round of applause too. Sounds like we have some psychologist parents in the world. Now, modern applications of sensation and perception. I have a friend. He's my very famous friend, Sliman Ben Zamea, who is up there at the University of Chicago, and he is actually trying to figure out how to interface bionic limbs with brains, so that he's trying to figure out how to program your brain to move your bionic fingers around. If any of you know, have a friend or anybody with a prosthetic limb, you'll notice that all they can do is move that limb around like this. They can't control the periphery of that. But my friend Sleeman is actually trying to figure out how to connect these bionic parts to the brain, and so that people can actually move their prosthetic limbs. Okay, cool. Well, I'd be curious to find out how he knew that, Omar. That's very impressive. And you know what? The military is also very interested in how we sense and perceive things. If you think about it, submarines are out looking for other submarines that might be attacking them. And how do you differentiate a submarine from a whale or a submarine from a school of fish? There's actually a branch of psychology called signal detection theory that actually has medical interest as well, that is interested in figuring out how we diagnose uh, uh, the signal from the noise. If you think about it, how many of you took a COVID test? Did any of you take a COVID test? Now, a COVID test looks for antibodies in your blood. If there's not enough antibodies, COVID virus in your blood, the test will miss it. And so you may actually have the virus, but you have so little of it that the test that is used can't actually diagnose and identify the virus in it. On the other hand, some of you may take tests that say you have a virus, even though you don't have the virus. Maybe the test gives you what's called a false positive. And so signal detection theory is all about trying to detect the real signal from noise. And it can be used in trying to detect submarines for the military, and it can also be used to detect low levels of virus or any other sort of disease or other sickness that you may have in your body. Okay, whoa. All right. Oh, they do shove it up the nose? That doesn't sound like a lot of fun, Ryan. Okay, so if you'll notice right below me, I've actually, just for your interest, I've got a set of absolute thresholds. So 1 teaspoon of sugar and 2 gallons of water is about the least amount of sugar you can taste. 1 drop of perfume in an entire 6-room apartment is what you can smell. So those of you who like perfume or aftershave, just remember, don't use so much stinking aftershave. 1 drop's all you need, right? Touch, a fly's wing falling on your cheek from a distance of a little over 4/100ths of an inch. The tick of a clock at 20 feet under quiet conditions. These are all absolute thresholds. But like I said, they change depending upon the environment. Now, let's go to the brain a little bit for just a section. We have 5 primary senses, so we have 5 primary sensory cortex. You have a somatosensory cortex located in your located in your parietal lobe. That's the blue stripe right here, right behind the motor cortex. You have a gustatory cortex and an olfactory cortex. Both of these are located in your frontal lobe. So your sense of smell is processed in your frontal lobe, and your sense of taste is processed in your frontal lobe as well. Your auditory cortex is located in your temporal lobe, and all the way at the back of your brain is your visual cortex, your primary visual cortex. It's sometimes called the striate cortex because if you look at it, it's actually striped. 1 stripe for your left eye, 1 stripe for your right eye. And so you'll notice that it's got lots of stripes. Stripes for your left eye and stripes for your right eye. Now, aside from these primary cortex, you also have association cortex, and those are areas of the brain that combine basic sensory experiences to help you form perceptions of objects. Not only when you look at this brain right here that I'm holding in front of you, not only do you notice the shape and the color, but that information then has to travel down to your temporal lobe where your memories are stored, and you have to be able to pull out the memory of what this object is that you are looking at. So your memory is connected to your visual senses. And all your senses are kind of connected together. You may see an orange, but at the same time you see an orange, you smell an orange, and you taste an orange. You know what I mean? And so all the senses work together. And in fact, don't get caught up thinking that your eyes are the only thing that can tell you what something is. So I want you to tell me, can you guess what the object is? If you look at it, it's red. If you hold it, it's smooth and round. If you bite it or smell it, it smells kind of sweet. And if you take a bite, it feels crunchy, tastes juicy, and maybe bitter or sweet, depending upon the object, the type of object that you eat. What is this object? Oh, there you go, Ryan. Good for you. How about a little applause for Ryan on that? Way to pick up. Caitlin, nice job. Second place. Got to be a little quicker on that keyboard, lady. Okay, good deal. So for the test, I do want you to be able to know these 5 cortices, okay? Now, here's the thing. All of your cortex, we talked about the thalamus in chapter 2. All of your senses are processed through your thalamus except your sense of smell. And I'm not sure, but I think it's because, evolutionarily speaking, your sense of smell might be one of the oldest senses that you have. So it actually developed before some of these other senses were well developed. And so that's the only sense that isn't processed through the thalamus. Okay? Now, let's talk a little bit about vision. Okay? Now, in the back of your eyeball, so you got some eyes right here. All right? Now, the little black dot that you see in your eye is called a pupil. It looks black, but basically what it is it's an opening. It's a hole in your eye. The reason it looks black is because light's not coming out of there, so it looks black. But if you took a flashlight and shined it in your friend's eye and looked inside their pupil, you would see the back of their eye, which is called their retina. All right? And the retina is at the back of your eyeball, and it's actually considered part of your central nervous system. And it's composed of these visual receptor cells called rods and cones. And rods and cones have these chemicals in them called opsins, O-P-S-I-N-S. And opsins is a chemical that generates an action potential when it is struck by light. So light comes into your eyeball. When it strikes these rods and cones, it activates this opsin, which generates nerve impulses. Remember, we talked about action potentials, right? And so you have 10 million of these rods and cones in your retina, all right? Now, you have 2 different kinds of visual receptor cells. You have rods and you have cones. Now, if you're looking straight at something, if you're looking right at the screen right now, I am falling on your fovea. That's where things fall when you look directly at something. So as I'm looking directly at you, Caitlin Pickett, okay, you are falling on my retina right now. And when you fall on my retina, you are falling mainly on these things called cone cells. Cone cells need a lot of light to work, okay? Their absolute threshold isn't as low as the rods, but they generate color vision. You actually have 3 different kinds of cone cells, and they respond to wavelengths, 3 different wavelengths, red, green, and blue. And that's what gives you your color vision, okay? Now, outside of your fovea, you have these visual receptor cells called rods. And rods are more sensitive to light. They work better in dark conditions, okay? So if you're walking around looking at night and you're walking around your bedroom and you see shapes of objects, you're going to know, what I want you to know is that your rods and cones are picking up the low level of light. Your rods are picking up the low level of light. Your cones are not working at all, okay, because they're not getting enough light to work. But your rods are working. However, your rods don't give you color vision. And so that's why at night, when you look at stuff, the colors you see, you don't see colors at night, but you see shades of gray. And that's because your cone cells, which generate light, which generate color, aren't working. Now, if you're in a dark room and you look at your red blanket, you probably think that you see a red blanket. It doesn't look quite as bright, but you say, you know what, I can see just a little bit of red. Actually, your cones aren't working. What's happening is at the perceptive process, at the end of your visual processing, your brain is adding in the color red because it knows your blanket should be red. It knows that your blanket should be red. Okay? So you've got these rods and cones. Now, After information, it turns out that you've got these rods and cones. You've got 10 million rods and cones, and they receive light input. And these opsins turn these light input into action potentials. You've got these things called ganglion cells. It turns out that although you've got 10 million rods and cones, you've only got 1 million nerve axons leaving your brain, leaving your eye and your optic nerve. And so the information that your rods and cones get is compressed by 10 times before it ever leaves your eye. So you've got these ganglion cells, and what happens is when a ganglion cell sees one color being activated, it actually inhibits the other color from being activated. Have any of you ever done one of those cool visual things where you look at a picture for 30 seconds and then you turn away and look at a white wall and you see the exact opposite color? Has anybody ever seen that before? I'm going to wait for a second and see if you get that, if anybody's seen that. Sort of this, okay, Phoebe, you've seen that. Yes. Well, what happens is when you're looking at the red light, if you look at a picture that's red for 30 seconds, okay, and then look away, what you'll see is a green after image. And what's happening there is when you're seeing red and your red cone cell is being activated, your ganglion cell is actually inhibiting your green cone cell from firing. It's not only leaving it alone, it's actually pushing it down so it can't respond to information. But after you look away and that red cell quits seeing red, the ganglion cell lets off the green cell, and the green cell actually pops back and it springs back a little more and gives you an imaginary green image. So ganglion cells in your eyeball actually help the rods and cones work together. Okay? Now, after the rods and cones are activated, they send the nerve out through this thing called an optic nerve. Now, it turns out that there are no rods and cones in your optic nerve, so that's actually what we call a blind spot. Now, so there's actually a hole in your vision. It's actually located right outside of center on either eye. And so there's a blind spot where you're not getting any visual input. However, because you have two eyes, each one is covering the other area, and so that way you don't see the blind spot in your eye. Now close one eye and you'll notice you still don't see that blind spot. You know why you don't see that blind spot? Because your brain fills in the missing information because it knows something is supposed to be there. Okay? Now, information leaves the optic nerve and heads back to the thalamus. So if you look at the picture right below me, you'll see that you have the thalamus and you have sort of a red line and a blue line. Okay? Now, it turns out that each eye sees the left half of your world and the right half of your world. Remember that word hemifield I used last week? So each eye sees the right side of my right eye sees my left world, and the right side of my left eye sees the right world. And the left side of my right eye sees my right world, and the left side of my left eye sees my right world. Does that make sense? You see the picture underneath here? And so each eye is seeing half of your world. But if you'll remember from the lecture I told you last week, when it gets to the back of your brain, the left half of your brain perceives your right world, and the right half of your brain perceives your left world. So the information coming from each eye has to switch to the correct hemisphere on the way back to the brain. And if you'll notice, there's this little X structure located in the picture right below me, and that's called your optic chiasm. And at that part, the information from the left half of each eye is shunted to your right brain, and the right side of each brain is shunted to your left eye. Does that make sense? So the optic chiasm is where visual information is finally separated. And so each eye is giving you a vision of your right world, and each eye is giving you a vision of your left world. And that information is put together back in your primary visual cortex. Now, if you look all the way over on the far left, you'll see there's a structure called the superior colliculus. Your superior colliculus is located at the back of your thalamus, and actually you can see it in the picture right below me. It's the two little yellow bumps at the very back of the thalamus. And your superior colliculus is the thalamic structure that allows the integration of your vision with your other senses. So, without your superior colliculus, you would be able to see your cell phone, but you wouldn't be able to pick it up. I see a stapler right in front of me, and I'm reaching it and I'm picking it up. The reason that I can pick it up is because my eyes are trained to be, or matched to my hands, so that I can reach around and pick it up. Now, there are people who have damage to their parietal lobe or damage to their superior colliculus, and these people can see objects in their environment, but they can't actually grab them. It's really weird. It's a disorder called ataxia. And these people will reach around and they can see it, but they can't quite grab it. It's really bizarre. Any questions so far? I hope this is making sense. Just check in, let me know you hear me. Okay. What controls depth perception? Great question, Lily. Great question. The fact that you have two different visions, a left eye and a right eye, okay? You have a left eye and a right eye, and they both see the left picture. Take your eye and put your finger out here, and you close one eye. And then close the other eye, and blink them back and forth. What do you notice about your finger when you close, you go from eye to eye? What happens to your finger? What do you notice about your finger when you switch eyeballs? What does your finger do? It looks like it moves. Exactly. That's because each one of your eyes is looking at your finger from a slightly different angle. And so this binocular disparity is actually calculated by your brain in your parietal lobe to give you a sense of depth perception. Your brain is doing math, and the more different the object looks, the closer it is to you, and your brain knows that. So these two eyes give you depth perception. Now, if you're blind in one eye, like Whitaker asks, that's a great question, you do not have this binocular disparity. And so your depth perception is going to be affected to some degree. And actually, you're probably not going to be able to play sports where they throw a ball at you. When I used to teach this in the classroom, I would bring eye patches and ping pong balls, and I would have my students put on the eye patches, and then I would throw ping pong balls at them and have fun, because the ping pong balls would always hit them because they couldn't catch them. And so if you are blind in one eye, and I'm not sure, I don't know enough about the DMV, but I'm not sure if being blind in one eye disqualifies you from having a driver's license. But one of the things that it does is it really impairs your depth perception. Now, here's the thing. It turns out that your brain also has these monocular depth clues too. So, for example, which is closer to the screen, my face or my hand? Can you folks tell me? Which is closer to the screen right now, my face or my hand? The hand. How did you know that? How did you know that, Luke and Kira? How did you know that? Bigger. Good one. And also, because you're smart. Well, I knew that, Whitaker. I knew that. Because the hand was covering my face, right? And so it turns out that your brain also learns visual cues to help you guess distance. But your true depth perception comes from the fact that you have two eyes, each seeing a slightly different image, or the image from a slightly different angle. Great question. I'd like to talk briefly about color vision. Okay? So it turns out that you have three different kinds of cones. And each of these cones has a different opsin that responds to light of different wavelengths. So, rods and cone cells, your visual receptor cells, are responsive to light wavelengths somewhere between 400 nanometers and 700 nanometers. We call that the visual light spectrum. If any of you are DC Comics fans, you probably know that Superman has X-ray vision. Superman has X-ray vision because he's a superhero. X-rays are bouncing in your eyes, but your eyes aren't sensitive to X-rays because it lies outside of the visible light spectrum. If any of you ever seen those infrared glasses that the military uses that allows you to see people at night, those night vision glasses, you can't see that because these heat signatures lie out of the visible spectrum. The only light that stimulates your eyes comes somewhere between 400 nanometers and 700 nanometers. I know, wouldn't that be cool, Whitaker? Now, your rod cells, which are not sensitive to different colors, respond to any wavelength between 400 and 700 nanometers. So any light coming from any of those wavelengths will cause your rod cells to activate. But your cone cells are very particular, and you have three different kinds of cone cells. Your S cones respond to light at the shortest end of the visible light spectrum, the blue light. Your M cones, your medium cones, respond to light in the middle of the visible light spectrum, and your L cones respond to light at the longest part, the longest end of the visible light spectrum. So you actually have three different cone cells that give you visions of blue, green, and red. Now, if any of you have ever been in an art class before, you know that you can mix colors. So red and blue make what? Red and yellow makes what? Right? So you can mix these colors. And so when you get different wavelengths are activated, your brain can generate different colors. So red and blue make purple. Red and yellow make orange, right? Exactly. They make different colors. Now, here's the thing. It turns out people who are born colorblind, there are people who are born colorblind. And these people are missing proteins that respond to the appropriate wavelength. So people who have red-green color blindness, they can't tell the difference between the red and the green spectrum. So they don't have a protein which allows them to differentiate the red light from the green light. They can see blue, but they can't see the difference between blue and red, but they can't see the difference between red and green. I hope that makes sense. Now, the bizarre thing is, some people actually, you can get damage to your occipital cortex. People aren't born this way, but some people get damage to V4, an area of their occipital cortex, and it takes away their ability to perceive any color. Their cones are still working, but when that information gets back to the back of their brain, they don't have V4, and that's the area that perceives colors. And so some people actually, it's called hemiachromatopsia. And imagine if half of your world was black and white. So I had color on this side of my visible spectrum, and this side looked like nothing but black and white. Now, people who are born colorblind, they don't see black and white. Instead, they just have difficulty differentiating between certain colors. But people who have brain damage may sometimes have hemiachromatopsia. Oh, really? Luke T. So Luke T's colorblind. That's interesting. What color do you have difficulty with, Luke? Now, so far I'm talking about sensation, okay? Red cones, green cones, and blue cones firing is a sensory process. Seeing lights, shapes, and lines and movement is what we would call sensation. But here's the thing. Vision is a two-step process. Not only do you sense stuff, but then you perceive things, all right? So not only do you see this object, you see its shape. So perception is seeing its shape. Perception is seeing its color. But then knowing that this is sensation is seeing the shape, seeing the color, and seeing the movement. Notice how it's moving. But perception is when you make meaning out of what you're seeing. Now, these psychologists, these German psychologists who became known as the Gestalt psychologists, they actually were the ones who founded my school, the social psychology school. They realized that vision is not just piecing things together, but creating holes in your brain. So you don't just see a black rectangle, you know that this is a cell phone, and you're able to see that. And you know what? Even though you don't see all of me, you know that I have legs, right? So if you're looking at my image right now, you don't see my legs or my arms, but you know you're seeing Dr. Roddenberry because you know that legs and arms are outside of your picture. Let me answer a question real quick. I don't think so, Whitaker. I think if you're missing the protein, it's genetic, and so that gene is going to function in both of your eyes. So I think if you're born congenitally colorblind, you're going to have the difficulty in both eyes. That's a really good question. That's a really good question. Okay. Now, it turns out that you can think of perception as two processes, bottom up and top down. Now, in bottom up processing, you look at the individual parts. You see my legs, you see my stomach, you see my arms, you see my face. You put all those things together and you say, hey, that's Dr. Roddenberry. That's what we call bottom up processing. But a lot of times, people start by just seeing part of a sensory experience and they fill in the rest of the details. We'll call that top-down processing. So you've seen a ton of triangles before, right? So if I show you a picture like this, right? Let me see, let me erase this again. If you see this, what do you see? What shape is this? What shape is this? Uh-oh, I'm sorry. Whiteboard. Oh, whiteboard. What shape is that right there that you're looking at? Can anybody tell me what shape that is? Or how about this? What shape is this? A circle. Exactly. And the other one is a square. Now here's the deal. If your sensory system worked in a bottom-up fashion only, you wouldn't be able to tell me that you were looking at a circle or a square. But the cool thing is your brain is able to add in the missing information so that you can figure out what it is you're supposed to be looking at. And it turns out that human beings have sort of these 5 basic principles that they use to fill in their world. Because if you think about it, you don't see everything in the world all the time. And you have to sort of use rules to group things together. Now, these rules are called proximity, similarity, continuity, closure, and illusory contours. For proximity, you don't see 15 dots. You instead see 3 groups of 5 dots. If I asked you what you saw, exactly, it's just like machine learning. Wow, great point. You feed the machine information and it begins to figure out things. That's a great analogy, Whitaker. Absolutely. In fact, you know what? I'm going to have to give you an award for that one. Good job. Okay? And so if you look at the first one, proximity, we tend to group things that are close to one another. So you don't see 15 dots, you see 3 groups of 5s. Now, if you look at B, we tend to group things by how similar they are. So you'll notice, to me, that looks like sand dunes coming up to an ocean. Do you folks see the sand dunes? Do you see the ocean water? Right? So you don't just see those shapes, you actually divide them based on similarity. If you're looking at C, you don't see a cylinder with 2 green squares on each side. You actually see a green bar that continues behind the pink cylinder. That's called continuity, right? We also know how to close objects out. So really you're looking at 3 V's, but you and I know that those 3 V's are supposed to be closed off and they make a triangle. And then for E, you'll notice that we see the illusory contour of a square. Even though really what I say you see are four Pac-Mans that are facing one another, your brain adds in the missing information so that you can see a square. Does that make sense? Ooh. Now, somebody, I think it was Whitaker, asked about what happens if you lose an eye. Can you see depth vision? You don't have true depth perception, but your brain has learned how to add in missing information to give you the perception of depth. And anybody who has ever drawn a painting can do this. And your book lists 6 monocular depth cues. These are depth cues that can be used with one eye to guess depth, right? So, let me go to my picture real quick. I'm a great artist, folks. You won't believe this. I am the greatest artist there ever was. So check this out. Which is behind, mountain A or B? Which is in front, mountain A or B? B is behind, exactly. Okay, fantastic. Let's see. That's what we would call occlusion, okay? Now, here's another one. How about this? Here's a road. Do you see how this road has depth? Because this is called the, exactly, B is behind, right? And so this is what we call the linear perspective. So you folks know that roads are parallel. So this is a road, so these edges of the road should be parallel, but as it goes off into the distance, they seem to join one another. This is called the linear perspective, okay? Now, here's another one. Which guy is closer, guy A or guy B? Uh-oh. Oh, crudola. There we go. See, guy A? Guy B is closer, absolutely, because he's bigger. Now, here's the deal. You know, relative size. These two guys should be the same size. But since one of them is much bigger, you know that there aren't 2-foot people and 5-foot people. We're all somewhere around the same. So because this guy is bigger, you know that somehow or another he must be closer to you than the guy who is farther away. And then we have this texture gradient. You know how all lines have those yellow lines? The roads have those yellow lines in the middle? As you go farther away, the texture appears to change and the texture gets closer together. And so, in a sense, you can use all these clues to create the perception of depth in a picture. Okay? Exactly. Oh, great point, Whitaker. They have that visual illusion where they put the people in the room that is not square. And because the room, you assume that the room is rectangular, but it's not. And it gives you the illusion that one person is a giant and one person is a little bitty person. That's a great point, Whitaker. I'm telling you, you were all over it today, Whitaker, with the good insights. Very well done. Exactly. All right. So, does everybody understand today's lecture? Okay, I want you to know what receptor cells are. I want you to know what transduction is. I want you to know how sensation and perception are different. I want you to know who Gustav Fechner was and what a difference threshold was. I want you to be able to tell me in which lobe each of the sensory cortices is. I want you to know that the sense of smell is the only one that doesn't go through the thalamus. Okay. I want you to know what rods do and what cones do. All right. I want you to know what the optic chiasm does and what the superior colliculus does. I want you to know why we have color vision and what happens, why people are colorblind. And I want you to understand the 5 principles of visual organization and I want you to know these six monocular depth cues. Okay, does anybody have any questions? Thank you very much for coming to lecture. 28 students on a Monday is absolutely fantastic. You folks are incredibly responsible. You're doing a great job this semester, and I am super happy to have you as my students this semester. Okay? Thank you for coming. Look, if anybody has any questions, don't hesitate to send me a text or an email. But outside of that, I'm going to go ahead and log off today, and I look forward to seeing you on Wednesday afternoon. Have a great day, folks.